32 pounds. That's all the force it takes to rip the tail off a passenger jet, less than what your suitcase weighs. On November 12, 2001, First Officer Sten Molin lifted an Airbus A300 off the runway at JFK Airport. 2 minutes later, 265 people were dead. Not from a terrorist attack, not from engine failure. It was because of a simple movement of his foot. A move he'd been taught for years was the right thing to do. The chilling part? The airline knew its training was flawed. The manufacturer knew its rudder pedals were a trap. And nobody said a word to anyone. Here's how it happened. Imagine being taught to drive a car the wrong way for years and having no idea. That's exactly what was happening to pilots at American Airlines for nearly a decade. The airline had its own advanced training program called AAMP, the Advanced Aircraft Maneuvering Program. It sounds impressive, and on paper, it all seemed to make sense. The program trained crews on how to handle wake turbulence, the invisible vortices of air that trail behind every heavy aircraft after takeoff. Flying into one of these is like hitting a horizontal tornado. The plane can be thrown into a sharp bank, and the pilot has just seconds to level the aircraft. But this is where the core of the problem lies. The AAMP program drilled one specific idea into its pilots. If the plane banks, you push the rudder pedals. Don't touch the yoke, don't use the ailerons, just stomp on the pedals. Instructors ran this scenario over and over in the simulators until the pilot's hands and feet learned the move by reflex. Muscle memory is a powerful thing, and that's what makes it so dangerous when it teaches you the wrong lesson. Meanwhile, the rest of the aviation world was teaching the exact opposite. You correct a bank with the ailerons and use the rudder gently in small, measured inputs. But the pilots at American Airlines didn't know this. They were confident they were being taught correctly because it was the official program of one of the world's largest airlines. But the flawed technique was only half the problem. The other half was hidden in the design of the aircraft itself, and almost no one knew about it. In the aviation world of the early 2000s, there was a convenient rule of thumb that almost every pilot believed in. It went something like this. As long as you're flying below maneuvering speed, which is about 270 knots, you can move the yoke and pedals as aggressively as you want, and the aircraft's structure will handle it. It was like an invincibility zone in a video game. As long as you were inside it, nothing could harm you. The problem is, this was a dangerous misconception. Maneuvering speed protects the aircraft from a single, abrupt control input, but not from a series of them, one after another, because each new input adds to the stress of the one before it. Now, let's talk about the plane. The Airbus A300-600 is equipped with a system called the RTLU, or Rudder Travel Limiter Unit. It works simply. The faster the plane flies, the less the rudder pedals can move. At low speeds, you can push a pedal several inches, but at 240 knots, the full range of motion shrinks to a mere inch. The idea seems logical. At high speed, even a small rudder deflection has a huge effect. But there was a catch that turned this system into a trap. The pedals became so sensitive that a light press of the foot would move the rudder almost to its maximum limit. And here's the unbelievable part. The flight crews were never told about this feature. So, picture this. A pilot with the wrong training is sitting in a cockpit with trap-like pedals, and the only thing standing between him and a catastrophe is the tail of the plane. Specifically, the vertical stabilizer, a massive fin as tall as a 3-story building that sticks up from the tail and keeps the plane from yawing side to side like a car on ice. On the Airbus A300-600, this fin isn't made of metal. It's made of a composite, essentially carbon fiber soaked in resin and baked into shape. The material is incredibly strong and lightweight, but it has one nasty characteristic. Metal will bend and groan before it fails, giving you a warning. But a composite will take the stress right up to its breaking point, and then it just snaps, all at once, like a glass ruler. This entire 30-foot fin is attached to the fuselage by just 6 lugs, 3 on each side, 6 points of contact holding a component that endures tons of aerodynamic force in flight. One more important detail. This specific aircraft had already been through an episode of severe turbulence in its past. After that incident, technicians had thoroughly inspected the stabilizer's attachment points and found not a single crack, not the slightest sign of damage. The plane was certified as fully airworthy and returned to service. According to all the paperwork and inspections, the aircraft was in perfect condition on the morning the crew began their pre-flight checks. November 12, 2001. JFK Airport, New York. It's been exactly 2 months and 1 day since the attacks of September 11th, and the city is still on edge. Every takeoff from this airport is a small test of courage for the passengers. Flight A300-600 is headed for Santo Domingo in the Dominican Republic. On board are 251 passengers and 9 crew members. Most of them are flying to visit relatives or are heading home. In the left seat is Captain Edward States, a seasoned pilot. Today he's the pilot monitoring. He's handling the instruments and radio communications. The controls are with First Officer Sten Mullen. He's the pilot flying, taking the aircraft from takeoff to landing. This is a standard division of duties, nothing out of the ordinary. The weather that day is nearly perfect for flying. Clear skies, good visibility, a steady, moderate wind. No storm fronts, no icing, no fog. For the controller in the tower, it's just another Monday, one flight out of dozens. At 2:13 and 27 seconds p.m., the tower clears them for takeoff, and the heavy Airbus begins its roll down the runway. Everything is normal. The engines spool up to take off power. The speed increases. In 2 minutes and 1 second from this moment, the cockpit will descend into chaos, but for now, the crew has no idea what's coming. But there is one detail the crew is aware of, but is underestimating. Just 100 seconds before their takeoff roll, a Japan Airlines Boeing 747, one of the heaviest passenger jets in the world, had departed from the very same runway. 400 tons of metal had just pushed through the air, and trailing behind each of its wingtips are 2 enormous invisible vortices. Imagine 2 horizontal tornadoes, slowly descending and spreading out. You can't see them on radar. No instrument in the cockpit can detect them, but they are hanging in the air, directly on the departure path. Flight A587 lifts off from the same runway and begins a standard left turn, the same departure procedure the Japanese jumbo jet had just flown. In essence, the Airbus is flying right into the aerial corridor, where a giant had passed just a minute before, leaving a turbulent wake in its trail. At 2:15 and 28 seconds, Captain States confirms the flaps and slats are retracted. The wing is clean. The aircraft is now climbing at a speed of about 250 knots. The crew knows there's a heavy aircraft ahead. The controller had warned them about wake turbulence, but they have the required separation. So, officially, everything is fine. The Airbus just keeps climbing, straight into the invisible corridor of swirling air. At 2:15 and 36 seconds, they make first contact. The Boeing is now 5 miles ahead and much higher, but its vortices have had time to sink right to the altitude of the Airbus. The plane flies through the edge of the wake, and the cockpit is jolted. The sensors record a brief spike in G-force, about 0.3 Gs, which feels like hitting a decent pothole on the road, nothing more. Captain States reacts calmly. For an experienced pilot, this is a routine event, a little chop on the way out of the airport. On the cockpit voice recorder, you can hear him casually comment on the turbulence, without a hint of concern in his voice. First Officer Moline shows no alarm either. The plane quickly stabilizes, and the climb continues as if nothing happened. But while the crew is relaxed, a mechanism they were never told about is already at work within the aircraft's systems. The Airbus's speed has reached 240 knots, and the rudder limiter system has now squeezed the pedal travel down to a single inch. That's about the width of your thumb. The entire difference between the rudder being neutral and being at its maximum deflection now fits into that tiny distance, and in 15 seconds, the plane will fly into the next vortex, which will be far more powerful than the first. 2:15 and 51 seconds, altitude 2,300 feet. The Airbus flies into the heart of the second vortex, and this time, it's far more than just a little turbulence. The invisible current grabs the aircraft and violently rolls it to the left. The bank angle instantly hits 25 degrees. For an airliner at such a low altitude, this is a very dangerous angle, and it needs to be corrected immediately. In that exact moment, everything he was taught for years on the simulator kicks in. Sten Moline doesn't reach for the yoke to use the ailerons. Instead, his foot automatically slams down on the right rudder pedal. This is precisely how he was trained to react to a bank caused by wake turbulence. His brain doesn't think, his body just acts, because muscle memory doesn't ask for permission. The simulator program Moline had been through countless times had just fired, exactly as it was designed to. And one fact makes this situation truly terrifying. At this speed, it only takes 32 pounds of force to push that rudder pedal all the way to its stop. That's about 15 kilograms, less than the weight of a carry-on bag. Any adult can easily generate that much force with one leg, without even trying. Right now, the only thing separating a normal flight from a catastrophic structural load is a tiny movement of a pilot's foot, a movement he doesn't even recognize as dangerous. And Moline pushes. The right pedal moves 1.5 inches to the right, then 1.7. That's already past the single inch the system allows for its full range of motion. The rudder slams almost to its limit, and the massive fin on the tail violently redirects the airflow to one side. The aircraft lurches, the bank starts to correct, but Moline doesn't stop. His foot immediately jumps to the left pedal, 1.7 inches in the opposite direction. The rudder instantly swings to the left, and the stabilizer gets hit by the airflow from the other side. Less than 2 seconds later, the right pedal is pressed again, this time 2 inches deep, even further, even more aggressive. And then comes the final input, the left pedal, 2.4 inches, the most powerful of all 4 movements. This all happens in less than 7 seconds. 4 times in a row, the rudder is thrown from side to side at a speed of 240 knots. To put that into perspective, it's like someone driving a car at full speed, yanking the steering wheel all the way to the left, then all the way to the right, and doing that 4 times in a row. Only here, instead of a car, it's 140 tons of flying metal and composite, and instead of asphalt, it's an oncoming airflow striking the tail with monstrous force with every turn of the rudder. These 4 pedal inputs do something to the plane that Moline can neither see nor feel from the cockpit. The Airbus starts to fly sideways. The nose is pointing one way, but the aircraft is moving another. This is called a side slip, and its angle is rapidly increasing to 12 degrees. Imagine a car driving down the highway at speed, but turned about 10 degrees sideways. The oncoming wind is pressing against its side with colossal force. The tail fin is taking the full brunt of this sideways airflow. Right now, it's not acting as a stabilizer, but as a giant sail turned perpendicular to the wind. The load on the 6 attachment lugs connecting it to the fuselage goes far beyond what any engineer ever designed for. The investigation would later show that if Moline had just taken his feet off the pedals after the second or even the third input, the structure would have held. There was still a margin of safety, but he doesn't. At 14:15 and 54 seconds, Moline shouts to the captain, demanding maximum engine thrust. He feels the plane is behaving abnormally and is trying to power out of the situation. States pushes the throttles forward, and exactly 2 seconds later, the cockpit voice recorder captures a sharp, loud sound that should never be heard in a normal flight. On the recording, it's a dry crack, like a thick, dry branch snapping, only many times louder. That's the sound of composite material failing. The carbon fiber, which held on until the very last moment, finally gives way. The first to fail is the right rear attachment point. The lug, through which tons of force are being channeled, tears apart, and a crack instantly races through the remaining points. Composite doesn't bend or warn, it simply shatters. At 14:15 and 58.5 seconds, the entire vertical stabilizer, 9 meters tall and weighing hundreds of kilograms, separates from the tail completely. Not a piece, not a fragment, but the whole component just rips off and falls away, like a torn fin. In a single second, the aircraft loses the one thing that kept it from spinning around its vertical axis. It's as if a car at full speed had its steering wheel and all 4 tires ripped off at the same time. At an altitude of 2,420 feet, the Airbus begins to spin uncontrollably and plummet. The yoke and pedals no longer do anything because there's nothing left to steer. 6 seconds after the separation, at 14:16 and 4 seconds, a piercing stall warning blares in the cockpit. The automation is screaming at the crew that the plane is falling, but there's nothing they can do. From there, the Airbus disintegrates in midair. The spinning and falling create G-forces that no civilian aircraft is designed to withstand. The fuselage is twisted and bent with such force that both engines are torn from their pylons under the wings. The multi-ton turbines, which were running at maximum thrust just seconds ago, are simply ripped from their mounts and fall to the ground, separate from the plane. On the air traffic controller's radar, the blip for flight A587 begins to lose altitude rapidly. The controller tries to make contact, but there's only silence. At 14:16 and 14.8 seconds, both black boxes, the voice recorder and the flight data recorder, stop recording simultaneously. This means the aircraft's power supply has completely failed. The last things captured on the tape are the sound of the alarm and fragments of the crew's words. The wreckage falls on the Belle Harbor neighborhood in Queens, a quiet residential area on the Rockaway Peninsula, just a few kilometers from the airport. One of the engines smashes through the roof of a house. The second lands at an intersection. The main part of the fuselage crashes onto beach 131st Street. From the moment it hit the wake vortex to the impact with the ground, less than 30 seconds passed. 265 people, everyone on board and several on the ground, would not return home that day. There were no survivors. While firefighters and rescue teams work at the crash site in Belle Harbor, the NTSB, the National Transportation Safety Board, America's lead agency for investigating aviation disasters, begins its work, and their very first discovery stumps the investigators. In Jamaica Bay, about 1.5 kilometers from the main crash site, fishermen spot a huge object in the water. It's the entire vertical stabilizer, that same 9-meter fin that tore off the tail. It's just floating on the surface of the bay, because composite material is lighter than water. But what stuns the investigators is something else. There isn't a single trace of fire on the part. No soot, no melted edges, no charred areas. The component looks as if it had been carefully removed from the aircraft in a factory hangar. For the NTSB, this means only one thing. The stabilizer separated long before the impact with the ground, while still in the air, when there was no fire. It fell separately and landed in the bay while the main wreckage continued its descent. When specialists examine the attachment lugs, they see the characteristic signs of a mechanical failure. The metal is stretched and torn by a monstrous force, not sheared or melted by heat. Thus begins the painstaking work of examining every square centimeter of the composite part, a process that must answer the ultimate question: why did the tail fall off a perfectly sound airplane? A corporate war begins, in which 265 lives become a bargaining chip between two giants. American Airlines claims Airbus is at fault, arguing that the pedal system was designed in such a way that a pilot could accidentally destroy the aircraft, making it a design flaw. Airbus fires back, claiming there was nothing wrong with the plane. It was American's insane training program that taught pilots to break tails with the pedals. Both sides hire armies of lawyers and engineers, and the public spat threatens to bury any objective truth. That's when the NTSB brings in the heavy artillery, specialists from NASA. The space agency's engineers receive the stabilizer wreckage and conduct a series of lab tests to understand one simple thing: was the composite material defective or not? The results turn out to be definitive and inconvenient for both sides. NASA determines that there was no manufacturing defect in the stabilizer. The composite was made correctly and withstood loads even higher than those required by certification standards. The part was stronger than the factory promised, but the forces unleashed upon it that day exceeded everything the structure was designed for. The stabilizer didn't fail because of a defect. It was simply ripped apart by aerodynamic pressure that should never exist in normal flight. In October of 2004, the NTSB publishes its final report, and its conclusions are harsh. The official cause of the crash was the in-flight separation of the vertical stabilizer as a result of excessive loads caused by the first officer's unnecessary and aggressive rudder pedal inputs. Put simply, the pilot broke the plane with the pedals, but the board doesn't stop there. It also points to a contributing factor: the high sensitivity of the rudder travel limiter system, which allowed a destructive load to be created with minimal foot pressure. In the aftermath, global changes begin that make this disaster a turning point for the entire industry. First, the aviation world finally debunks the myth of maneuvering speed. For decades, pilots believed that below this speed, they could move the controls as aggressively as they wanted. Now, textbooks include a clear warning. A series of sharp control inputs can destroy the airframe even at low speeds, because the loads accumulate. The operating manuals for all aircraft types are updated with a direct and unambiguous prohibition. Never apply full alternating rudder inputs. The AAMP program is completely overhauled, and the key element that led to the tragedy is struck from it: the use of the rudder to correct for roll. Pilots are now retaught what was correct all along. Roll is corrected with the ailerons, and the pedals are to be used gently and only when absolutely necessary.